Welcome to aminacademy.com. In discrete mathematics, let us discuss about Chinese remainder theorem. In mathematics, the Chinese remainder theorem states that if one knows the remainders of the Euclidean division of an integer n by several integers, then one can determine uniquely the remainder of the division of n by the product of these integers under the condition that the divisors are pairwise coprime. No two divisors share a common factor other than 1. It's called a coprime. For example, if we know the remainder of n divided by 3 is 2, the remainder of n divided by 5 is 3, and the remainder of n divided by 7 is 2. For example, n is some number. Then without knowing the value of n, we can determine that the remainder of n divided by 105, because we have to multiply those numbers. That is 3 into 5 into 7 is 105. The product of 3, 5, 7 is 105. That here, that n is here 23. Importantly, this tells us that if n is natural number less than 105, then 23 is the only possible value of n. The earliest known statement of the theorem is by the Chinese mathematician Sun Tzu in the Sun Tzu Xuan, China, in the 3rd century. The Chinese remainder theorem is widely used for computing with large integers, as it allows replacing computation for which one knows a bound on the size of the result by the several similar computation of small integers. Further explanation of the theorem. Let m and n be relatively prime positive integers. For all integers a and b, the pair of congruence equations are x is congruent to a mod m, x is congruent to b mod n, has a solution, and this solution is uniquely determined modulo mn. What is the important here is that m and n are relatively prime. There are no constraints at all on a and b. Here the congruence, for example, congruence x congruent 6 mod 9 and x congruent 4 mod 11 hold when x is 15, and more generally when x is 15 mod 99, and they do not hold for other x. The modulus 99 is 9 into 11. Here these are some explanation regarding the theorem, but we can understand clearly by using some example problem by solving. Example, find an integer which is unknown. When divided by 3, the remainder is 2. When divided by 5, the remainder is 3. When divided by 7, the remainder is 3. The remainder is 2. What will be the number? That means this 3 combination is given. First, the system of congruence. You can write the system of congruence. Can be written in the given information, that is x some number is congruent to 2 mod 3. That first sentence, look at here. When divided by 3, the remainder is 2. Some number is divided by 3, remainder is 2. We can write as x modulus congruent to 2 mod 3. Like the second, and when divided by 7, the remainder is 2. That is x, that second equation is divided by 5, remainder is 2. That is second combination is when divided by 5, the remainder is 3. Mod 5. That combination is congruence x congruent. When divided by 7, the remainder is 2. Remainder is 2 divided by 7. Mod. So this is a 3 combination equation. We have to solve this. Here, let m, that mode, general mode is 3 into 5 into 7, because we have to multiply these each modes. 3, 5, 7 is 105. Now capital M1 is m over 3, which is equal 105 over 3 is 35. Like that, M2 m over 5. M over 5 is 105 over 5 is 21. M3 equal m over 7, that is 105 over 7, which gives 15. So we got capital M1, M2, M3, which is useful in Chinese remainder theorem. Now we know that two is here. We know that 2 is an inverse. 2 is an inverse. 2 is an inverse of M1 equal 35 mod 3. Mod 3, which is equal M2 then mod, therefore mod 3, which is because, look at here, because 35 into 2 congruent to 2 into 2 mod 3. Here 35 into 2 is 70. 70 is divided by 3 is that remainder 1, so it's inverse. Then here, which is equal 2 into 2 mod 3, because 35 is divided by 3 is remainder is 2, and this 2 into 2, 2 into 2 is 4, divided by 3 is 1, so remainder 1, so it's inverse modulo. Then 1 is second, 1 is an inverse. 1 is an inverse. 1 is an inverse of M2, which is equal 21 mod 5. Since because 21 can be written as 21 is congruent to 1 mod 5, which means 21 is divided by 5, remainder is 1, and 1 is an inverse of 1 is an inverse of 1 is inverse of M3 equal 15 mod 7, because can say 15 is congruent to 1 mod 7. Therefore, the solution to the system can be written as x equal a1 m1 y1 plus a2 m2 y2 plus a3. Three system is here, a3 m3 y3. We are substituting the values. 2 into 35 into 2. Here 2 into 35 into 2, because 2 into 35 into 2 plus 3 into 21 into 1 plus 2 into 15 into 1. All of it got from this combination. Here, which is simplification, we get 233, because 27 is 30, 27 is 140, 3 into 21 is 66, 2 into 15 is 30, adding up together is 233. Mod 23, because of mod 105. Suppose 233 divided by 105 is 210. The remainder is 23. That is here 23. The remainder is 23. Therefore, it follows that 23 is the smallest positive integer, that is simultaneous solution. Therefore, 23 is the smallest positive integer. 23 is the smallest positive integer. It is the smallest positive integer, which is divided by positive integer divided by 3 divided by 23. Smallest positive integer leaves the remainder 2 when divided by 3, and a remainder 3 when divided by 5, and a remainder 2 when divided by 7. That means our solution, that is x is 23. If you put the 23, you can get the all solution simultaneously. That is, instead of x, we can write 23 equal 23 congruent to mod 3. Means if we divide 23 by 3, 23 divided by 2, remainder is 2. Same, 23 is congruent to 3 mod 5. Means 4 5s are 20 and remainder is 3. Same, 23 is congruent to 2 mod 7, which means if we divide by 23 divided by 7 is 23, 7s are 21, remainder is 2. So this is the solution of the equation, that is x is the solution, x is 23. If you have done, please subscribe our YouTube channel.